So, looking at a multiple slit diffraction grating, so one that has several thousand little gaps for the waves to go through. We've previously used that to produce an interference pattern by using a 2000 lines per centimetre grating. We saw the interference pattern on the screen here. We saw areas of light and areas of dark to indicate maxima and minima, constructive and destructive interference. Those lines on a diffraction grating are evenly spaced out, so the spacing between those never changes. We can use that knowledge to figure out an equation for using a diffraction grating. If we look at just one little gap between two slits on that diffraction grating, we've got two different rays going through there. D is the distance between where those waves originate, or where those rays originate. We just did a little bit of simple trigonometry, built a triangle here. One side is path difference, this side is the distance between the slits. The theta is the angle of deviation, so the angle that you move upwards from the normal line, which is at 90 degrees to where the waves are originating from. By using just the sine rule there, we can figure out that the path difference is equivalent to d sine theta. We already know that the path difference for a maxima is n lambda, in other words, multiples of 1, 1, 2, 3, or 4 for constructive interference to happen. So we can say that n lambda, the path difference, is equal to d sine theta. D is the separation of the slits, theta is the angle of deviation that's from the normal. N, as before, is the order of maximum, and lambda is the wavelength of the light that is going through at that particular point. So we can use this formula, we used it to figure out what the wavelength of the laser was. The important thing to note here is that in order to calculate the separation of the slits, we need to know how many lines we have per meter. So in this case, we've got 2000 lines per centimetre, so it's a factor of 100 more for a metre, so 200,000 lines per metre, and then we do 1 over that value to figure out what the separation of just two of the slits are. So we're really looking at an equation which is that's not given in the data booklet, but that's the generally recognised equation for this kind of stuff. So it's 1 over the number of lines per metre to calculate how far apart two of those slits are. We then applied that logic to a diffraction grating with white light. We know already that the wavelength of red light is 700 nanometers, the wavelength of violet light is 400 nanometers. So just by applying some simple maths, we can figure out why red deviates more. It's because the order of the maximum is the same, the wavelength is greater, the separation of the slits is the same, so therefore the angle of deviation must be more. Apply the same logic to if we choose a different diffraction grating with more lines. You've got more lines, so therefore your slit separation decreases. So if that decreases, then sine theta increases. So we're going to get more deviation from the normal with a diffraction grating that has more lines on it. Just use this example to highlight which angle it is we're actually measuring. As before, we calculate D by using 1 over the number of lines per meter. That gives us the separation of two of the slits on the diffraction grating, which is what we need to know. We use the diffraction grating equation for red light by substituting 700 nanometers in there to figure out how far it is to red light. So our angle of deviation to red light is here. We then use the same for violet light. Our angle of deviation for violet light is from the normal to here. So in order to calculate this angle in between, we subtracted the difference and get the angle there.